Here, looking at endo and exothermic reactions. So when a reaction occurs, few things happen. First, we need to break these bonds, and then these new bonds need to form. And when this occurs, well, or for this to occur, a couple things need to happen. One, we need some energy to break those bonds, because how else are they? They're not just going to fall apart, or else this would happen all the time. So there's a whole bunch of calculations you can do for this. We're not going to worry about that here, but just to give you an idea, some values. So to break an H bonded with an H, or to break that double O bond for the O2 molecule, takes 430, 495 kilojoules per mole. We'll talk about that later. Same thing here. When energy is released, well, energy is released when these bonds form, and there's values in a book and a table, or you can look them up, how much energy is released. So for one of these OH bonds in water to form, you get this much. And for this reaction, we'll talk about the fancy words and all that go along with this, but for this reaction, it actually makes, you get a net gain of 509 kilojoules per mole, meaning energy was actually released. We got more out than what we put in, and we'll talk about what that means coming up here. In some reactions, the energy that must be absorbed to break the bonds is less than the energy released. So if we look at the reactants versus the products, in this case, it takes less energy here, so we're actually going to release some energy, and we're going to release this much. And this is reaction diagram. We'll draw them at some point. And then above the curve here, something we call activation energy. So this is to get those reactants, to get those bonds to break. This is how much energy we need to put in. And if we can't get up that hill, if we don't give it enough, well, it's not going to occur. But this is what we call an exothermic reaction, where this energy is less than how much we get out. So meaning this is going to feel warm. It's releasing energy to the surroundings. The opposite is true for endothermic reactions. So in others, the energy that must be absorbed to break this. So this, you can see here, we have to absorb a ton of energy to break the bonds. And then when we release it, well, it's less than that. So in this case, it absorbs more energy than it releases. So on our diagram here, you can see how much energy is absorbed. You can see there the activation energy is much higher, because again, to get those bonds to break, we have to add a lot in, and then not a whole lot is given out. So this is an endothermic reaction. These would feel cold because they're stealing energy from things. So if you touched it, it's stealing energy from your hand. So exothermic reactions, these release energy in the form of heat or light, as we said. So these feel warm. An example of this in lab, if you would have touched that zinc and hydrochloric acid test tube, you would have felt it being warm. Any combustion reaction, you're burning something, it's releasing heat and light. If you were to mix, and this really isn't a reaction, you're just dissolving sodium hydroxide in water, that's a pretty exothermic reaction. That flask gets really warm. And then just kind of an everyday, maybe not an everyday occurrence, but a practical use of this is hand warmers. Hand warmers, if you ever, depending on what kind you get too, but next time you have one, kind of feel that white packet. You feel just kind of like grains or something like that. Those are just grains of iron. And when you open the plastic container that they're in, that's oxygen. Well, that allows oxygen in through that white kind of paper barrier, cloth barrier, and all you're doing is forming rust in there. Now there's a catalyst in there to keep this at a certain rate and things like that, but that's how hand warmers work. It's really the reaction of iron and oxygen to make iron oxide to make rust. So practical application there for exothermic reactions. Keeps your hands warm when it's cold outside. And then lastly here, endothermic reactions, so a little more on those. Absorb energy in the form of heat or light. So these are going to feel cold. Practical application there, ice packs. Again, a couple different kinds, but two chemicals in there. You break the container on the inside, chemicals mix, and then, well, they start stealing heat from the atmosphere, or you put it on your leg or your arm or wherever you hurt, and it starts stealing energy from your body, and that's what causes it to feel cold. Another one, sodium bicarbonate, baking soda mixed with acid. Hydrochloric acid would feel cold as well. And then the last one, something you may not think of, but photosynthesis. So that's the reaction of carbon dioxide and water. Well, it takes light from the sun, but then we get out some products, some useful products for plants especially, but it's endothermic in the fact that it absorbs energy to make those products. And then the last one, just from those diagrams, a little bit more about activation energy. So this is the energy level the reaction must overcome. So how much energy you have to put into it before that can start making products.